Okay, folks, let's make this the one. First, start the pen going. Here we go. There we go. Welcome back. We're going to wrap up chapter 3 with differentials and a little bit of marginal analysis that we've already talked about several times. Remember marginal revenue, marginal cost, marginal profit? Yes. You might remember that a little bit. So we're going to talk about differentials of functions in general, especially in economics about the revenue, cost, and profit. And then we'll wrap it up with a few formulas for differentiation that'll look really familiar, even though we'll be using them for differentials. So here we go. First of all, you might remember that when we began back in chapter 2, we talked about the ratio delta y over delta x. Remember that? That was in the definition of the actual derivative itself. Does this look familiar? Sure it does. We used that in section 2-1, if you remember, when we started the derivative chapter. Now, the dy dx isn't interpreted with the dy and dx being separate. Remember we talked about f prime of x, if you want to write it that way, but an alternate way of writing it was dy dx, and maybe if you were thinking a little bit too much, you might have thought, well, why make a fraction out of it when I can just write f prime of x or just y prime? Well, yes, you're right. But dy dx is pretty handy too, because we can actually go back to this delta y over delta x and think of this as sort of almost the same thing as dy dx. Actually, the other way around is more like it. The dy dx is similar to delta y over delta x. They're not exactly the same though. The delta y over delta x, you might want to write this down. This is the exact change when you go from point 1 to point 2. These are the changes in the y coordinates and the change in the x coordinates. Of course, dx can't be 0. But remember, first, delta x and dx are the same. Put that down in ink or whatever you need to. However, delta y is close but not quite the same as dy. And we'll show you why. So the differential of y. So let's start by writing the derivative like this. And just for convenience, we're going to say dy dx equals f prime of x. Now, all we have to do to slide in the differentials is think of dx as being a separate number. So if we think of this as a real denominator number, multiply both sides by a dx. And what you'll have is on the left side, the dx's will cancel, and you'll have equals f prime of x times that dx we multiply both sides by. And this is what we're going to be using to do some really neat stuff, and easy too. So this is what I just told you. dx and delta x, same thing. But if you look at the picture here, now you can see right here, dx and delta x identical. But remember, this is the function we're talking about, this solid line, or solid curve, excuse me. So dy dx we talk about with dy and dx. that gives us a slope, but delta dy coming from the tangent is not the same as the actual change in y. There will be a difference between the two. The good thing is this difference, thanks to limits, for example, is going to be very small. And this is going to be very handy, enabling us to do some things that might be quite tedious otherwise. You'll see what I mean later. So this change in y is defined this way. Now, this second part right here is the actual y value at the point we're interested in. The one that's here is a y value that's close to it at the second coordinate, the second point. So how does this work? Well, we've got the picture here so you can see it. If we bring this point right here a little bit closer, then dx equals delta x is exactly the same as it was before. They are the same. But the closer this point is to the original point, the smaller the difference is going to be between dy and delta y. Here this delta y is this big and the dy is that big. Not very close. If we bring this point right here closer to the original point there, the difference between those two won't be as great. So take a look at this. The tangent line approximation, that's this tangent line right here, is the basis for most applications of differentials. In other words, in going from this point somewhere over here to another point, we'll get a second point, but we'll be able to use this tangent line to get us from this point to one that's close to it, because it'll be almost the same as the one for the actual curve. If you look right here, for example, let me clear this so you can see this. This is the original point here. If we're not too far away, say at this point right here, it's almost indistinguishable between the two y values, the delta y and the dy. They're almost exactly the same here. This distance versus this distance, almost no difference, as you'll see when we get to our first example. The point is, the graph of f, that's the solid line, is very close to the tangent line, very close around here. Out here, there's a big difference between the two. See those? Not really close, but here, they're rather close to each other, the tangent line and the actual graph itself. So the approximations used in this system, in this section, use this situation with the two being close to each other. So let's get to a real example and you'll get a better idea of what's going on. So we take our old buddy, the quadratic function, the simple quadratic function, just x squared, and we'll see how this goes. So first of all, here's the question. Find dy. So we're looking for this when x equals 1 and dx equals 0.01. We're going to compare the value of delta y with dy when x equals 1 and delta x is 0.01. Okay, what am I talking about? First of all, let's work on dy. First of all, we'll take this function, x squared, and we'll take the derivative of that function we're calling f. So there's our derivative, our first derivative, and that's all we're going to go, just first derivative. Next, we'll multiply both sides by x. Miss that? There's our f prime of x. Remember, this is the same thing as dy dx. Now I'll multiply both sides by dx, and now we have this. That's our differential equation. Now this was the question. When x equals 1 and dx equals 0.01, what is dy equal to? Well, guess what? For one time only, perhaps, this is rather easy. All you have to do is put those things in. The x equals 1, that's going to go in here. The dx is going to go in here, like that. The 1 goes in to the derivative. You're going to figure out this, and you're going to multiply it by delta x, or dx. Remember, we had 2x, and the x is the 1. So you have 2 times 1 times that delta x, or dx. Just multiply it out, and there is delta y, excuse me, there is dy. Now, remember, we just found that dy is 0.02. Now we're going to find out what delta y is. Remember, I told you, usually it's pretty close. We'll see how close it is in this case. So delta y is the y value at 2 different places. Now we're talking where x equals 1 and delta x is 0.01. What's that mean? Well, first of all, take the easy part. X equals 1, f of x is just f of 1. We're going to find that easily. Now what's this other thing? Well, this says x plus delta x. X is 1, delta x is 0.01. Just add those two together and give them to our function. So the function value at 1.01, remember what f of x was? It was x squared. Excuse me. So we're going to take that 1.01, just square it. And over here, we're just going to use 1 and square it. Just like that. Now we'll multiply it and do the subtraction. And this is delta y versus dy. Delta y is the subtraction of 2 y values, or 2 function values. Dy you get from your derivative. See how close they are? 0.02 versus 0.0201. There's a picture. Here's the point we're interested in. And here's our delta x, or dx. 0.01 right there. Now, if you need to, look at that a couple of times. That's one of the values of the video lectures. We're going to take a look at some marginal analysis. That might actually help. So let's talk about revenue. So another way of writing this would be revenue is a function of x. X represents the number of items you're selling, and it's some kind of a function of x. Now, what we're talking about with these differentials is typically when x increases by 1, that makes delta x 1. You're going from like a 16 to a 17. x1 to x2. Just difference of 1. Two different x's. Now, what we're going to do is we're going to find what happens with the revenue change. Well, delta R is the difference between the function values or the revenue values at two different parts versus what dr says from our using calculus. Remember dr? Well, we might like this better. This is what you would have to begin with, dr dx, and you can call this dr dx, or you can call it f of x, or you can call it r prime of x. Multiply dx times both sides, and that's what you got, where this is r prime. So let's use the differential to see the change. You can also do the same thing for cost. You can do the same thing for profit. So here's one for us to play with. Here's a profit function, p of x, and it's 0.0002 x cubed plus 10x for this particular example. So first of all, we're going to find the differential dp to approximate the change when we go from 50 to 51 units. We're making and selling 50 units. We're going to see what happens to the revenue, or the profit in this case, when we switch and we make one more item, whatever that item is. And then we're going to look at what the actual gain is, because this is going to be a good approximation, but it's not necessarily always the same. So here's how it works. So remember, we had p of x was 0.0002 x cubed plus 10x, remember? And this is the derivative with respect to x. Now, what are we going to do? We're going from 50 to 51. That's a difference of one item. So what is the approximate change in profit? Well, it's going to be approximately dp. Well, dp dx times dx is dp. Here's dp dx. We just found that up here. dx is our change in x. We're going from 50 to 51. That'll be a difference of 1. So here's what we've got with our calculus, and we'll evaluate that. So if we increase the production from 50 to 51 units, our profit will be increased by $11.50 according to the calculus. Now, what is the actual change from going from 50 units to 51 units? Well, let's see. First of all, this is our original function. We're going to evaluate it for 50, and then we'll evaluate it for 51. That's how it works. And we're going to find out how much extra profit we get from going from 50 to 51 units of whatever we're selling. So this one, remember, is 51. So put the 51 in where the x is in our derivative. or our function rather. This one. Put the 51 in, and this is what you'll get. Put the 50 in, and this is what you'll get in this function. And we're going to subtract and see what the difference is, what the increase is. There are two values, subtract them, and the difference is $11.53. This is the actual difference for us, delta y, or delta r in this case. This is dp, or delta y. Notice it's close. This is the real difference between those two levels, and this is our quick approximation using calculus. Here's a picture that you can take a look at. This curve or line right here, when we have small dx's or small delta x's, our curve looks almost like a straight line or a tangent. It's not exactly, but it's close enough for us. This is what it looks like visually. Remember, this is what we got from subtracting the actual values for profit. And this is what we got by using the calculus. All right, let's wrap it up with a little bit of practice for differentials before you actually get to work. So grab a piece of paper and get ready to hit the pause button occasionally. Here are some formulas. They should look a little bit familiar. This one should remind you of dy dx. We have f of cx, dy dx, and that c, which is a constant, is just brought out front. This and this look about the same. You just move that c out front. The second part says you can take those individual parts and take the derivative of each one, but now you've got a differential equation instead of a straight derivative. If you go back and compare those, you'll see the difference. Now this one was dy dx for f1, oops. Let me write that again. If y is f of x plus g of x, then taking the derivative of y, you just take the derivative of each of the individual parts. Or if it's minus, same thing. Next one, this is the product rule. It should look familiar. If you've got two functions like this, where y equals f of x times g of x. Remember, you had f of x times g prime of x plus f prime of x g of x. Compare that with this. Here's one function, here's the other function. Each is multiplied times the derivative of the other one. Well, now it's, instead of derivatives, it's differentials. This should look familiar too. Here's the function in the denominator right there. And there's the one in the numerator right there. So here's the lower times the derivative of the top minus, because it's the quotient rule, the numerator times the derivative of the denominator. And then the denominator squared. Is that ringing a bell now? The constant rule, same as before. Remember, if y equals 4, y prime is 0. The same thing applies with the differentials. In the power rule, bring that exponent out front and reduce the exponent by 1. Sound familiar? It's really the same, except you take the derivative, multiply both sides by dx or whatever is in the denominator. Okay, some practice. First of all, here we've got a function. Now, we go through the first one. I think you'll get the idea. And then you can pause a few times on the other ones that we're doing. See if you can do them ahead of time. So here's y equals x squared, our old buddy, the basic parabola. There's the derivative. Bring that 2 out front, reduce 2 by 1, 2x. Now what's new? The differential. Multiply both sides of this by dx, and there you've got your differential. Let's try another one. Here's another function. The derivative of that is, good practice, come on, hit the pause, try it, then check. You should get dy dx equals 3/5. If necessary, rewrite this as y equals 3/5 x plus 2/5. And there you've got a constant, and there you've got 3/5 x, and the x, the derivative of the x alone is 1. And the differential, just multiply both sides by dx, and you got your differential. And you'll very quickly get an estimate for what delta y is by just using dy. Next, let's try this one. Okay, hit the pause button this time if you haven't already. Change that or convert that to a derivative, and then it's differential. Okay, you're back. There's your derivative, and there's your differential. Getting a little bit more comfortable with it? Next one. There's another one. Oh yes, a fraction. Of course, I'd have to throw the fraction at you, right? Take the derivative of that. Should have this. It might even look familiar by this time. And what's the differential? Just multiply both sides by dx. And there you go. Well, that's a start on differentials for you. You take it from here, and I'll see you next time. Take care.